So we're finishing up chapter P, and think about what we've been through so far, the chapters we've looked at, the topics. Appendix C was pre-calculus topics. It's taking pre-calculus really and almost squeezing it into a week's time. Chapter P is preparation for calculus. So it's really still pre-calculus, and we're getting ready to do calculus. When we get to chapter 1, then all of a sudden we're talking about previewing calculus. So when are we going to do calculus? Soon. We will. But there are some topics here in section P3 I think are very important. This section deals with functions and the graphs of these functions, function notation, evaluating functions, piecewise defined functions, and more importantly, domain and range, and what they are, and how to determine domain and range on a function. And finally, we'll graph functions, and we'll use the vertical line test to prove that indeed the relationship is a function. So first of all, it's important to note that a function is a relation between domain and range. So a function is a relationship between x's and y's. So what's going on here is you've got this big set of numbers that we refer to as the domain. In the domain are real numbers. We're sticking with real valued functions right now. And these real valued functions are x's. So there could be all sorts of stuff in here. 1, 2, 3, -4, pi is in there, 1/2 is in there, 0's in there. They're all here. Okay? So, over here is another set of real numbers. This is referred to as the range. In the range live all of our output y values. You can think of the domain as your input to the problem and your range as your output. Now in here also are real numbers. And I got to tell you that it's not that all real numbers show up in these bubbles. It's not necessarily true. But for now, we'll put all real numbers in here. -1, -3. Now, your function is almost like a transporter mechanism, and it takes numbers from here, and it kind of beams them over to numbers over here. Let's connect the 2 with the 0. And that's the function that does that. Let's take another look at this number 3, which is in the domain, and our function might connect it with maybe this number right here. And our function is what does that connection or transport. So I'm going to put a couple of negative numbers in here, -8 and -9. -7 might come over here and connect with the number -9, and that's our function doing that work. So a function is a connection or a relationship between x's and y's, but it's a very specific relationship. In fact, for this one, the relationship is y is equal to x minus 2. So x is your independent variable, y is your dependent variable, and y depends on your choice of x. For this example, any choice of x goes in here. 2 is taken away, and you get 2 less than that. 2, take away 2, you get 0. 3, take away 2, you get 1. So all of those mapping should be -2. Okay. Now, this is a function in explicit form. Here's another one. This is where the y output value is explicitly told to you. If you give it an input x, you simply need to plug it in, and y can be computed directly. So y in this case will be 52. Now you can also list this as an ordered pair. 7, 52 is your ordered pair that also represents what the function is doing to those inputs x. That's explicit form. Explicit form will always start as y equals. Another thing about explicit form, you won't see any y's on the other side. It's all x's. So we could do x squared minus x plus 1. That's fine too. For any given value of x, we should only get one output value, y. Let's see what we get on this one. Okay, we get 3. So the ordered pair would be -1, comma 3, again, an ordered pair x and y that relate the two variables together. Now, I did mention something as I was doing that that's really important when it comes to functions, and that is any given value of x that you put into the function is only supposed to output one value of y. So if I put x equals -1 in, I'm supposed to get 3 in this particular function. Anytime I do it, no matter how many times I do it, I always get 3. Now, there are relationships where you do get two different y values. In those relationships, we would say those are not considered to be functions. Here is an implied form, implicit form. This form looks something like this. This is a function, but it's an implicit form. It's just not as obvious as to what the y value is when you're given an x value. So, hey, you can choose any x value you want. Let's choose x equals -1 again. So we don't know y yet, but we sure know x. But all this better tally up to 0. So, sorry, I'm supposed to put my x in there. That's a 1. -1, I apologize. So we have y -1 minus another 1 minus a third 1 is supposed to be 0. So y -3, you see it took more work to get to the result. Y is equal to 3. So this is implicit form when the y is just simply not stated straight out front. Y equals. That's explicit form, and there can be no y's on the other side. Now we can solve from implicit form into explicit form pretty readily. That is a function. For any given value of x, there is only one magic value of y that makes the equation true. But the way to figure that out is to rewrite it in explicit form by adding the x squared over here and taking the 3x away from here. And now it just pretty much spells it out for you. Y is this calculation over here. And so now I could say x equals 1, and y, therefore, would be 11. The ordered pair would be 111. For every given value of x, there is only one valid output for y. We call this a one-to-one relationship. For every given value of x, there is only one valid output value for y. Now, what about things that are not functions? Let's give it an x value. So y squared is equal to 9. And if you take the square root of both sides, I hope you remember that one side needs a plus or minus. And then you get y equals plus or minus 3. So which is it? Plus 3 or minus 3? It can't make up its mind. So we do not have a 1-to-1 relationship. We have a 1-to-2 relationship. And that's just not going to work in terms of being a function. This is not a function. So y squared, when you see y squared, that's usually a giveaway that it is not considered to be a function. Y cubed is actually okay. Let's try y cubed is, how about 10 minus x? Let's pick a value of x. Just an example value, like x equals 2, for example. And let's see if there's one and only one value of y for that. So y cubed is 10 minus 2. Y cubed is 8. Take the cube root of both sides. There is no plus or minus when you do that, by the way. And there is one and only one value of y. That's 2. So we get 2, comma 2. And you can try any value of x that you like. You will always get just one corresponding value of y. Now this is still in implicit form. The only way to get explicit form is to have it state y equals. So it's very explicit. So let's take the cube root of both sides now. And now it's in explicit form. In fact, y equals the cube root of 10 minus x, and this is a great opportunity to write it using function notation. Now, function notation recognizes that all of your functions start with y equals, if they're in explicit form. So instead of using y all the time, we use letters like f, g, and h. In fact, let's use the letter f instead of my y. Next to the f, we put parentheses, and we put a letter x inside. Now, be careful, that is not f times x. X is just sitting in there reminding us that x is your input to the problem. X is your input, and your output is over here. So if you wanted your input x to be equal to 2, and you wanted to try that, on this particular function, you would say the f of 2. Now notice I just replaced x with the number 2, so of course over here I'm going to do the same. I'm going to replace the letter x with the number 2. So the f of 2 is equal to the cube root of 8, which just happens to be equal to 2. What's great about function notation is that you can see both the input and the output right here on the same page. So here's my input. That's a reminder, more or less, as what x was. And here's my output. And that's an explicit statement as to what y will be. And then we can combine them together again as an ordered pair. So that's your function notation. And also, if I were to provide you with a function definition, I do always want us to start with the f of x. And over here, you kind of describe what you're going to do to that x. You're going to square the x and then double that result. You're going to take 3 multiplied by the x and then maybe subtract 4 from all of that. Now you can pretty much put whatever you want into that function. You can put a number in if you want, like that, and get an actual result. And the ordered pair would be 1, 1. By the way, x and y are not always the same. It's just working out that way right now. But you can put other stuff in. Like, let's put the letter c in. I just replaced the letter x with the letter c. I am going to replace the letter x with the letter c. And that's about all I can do with that one because I don't know the value of c. I can also replace the letter x with other stuff, like you can put 2x in there. You can put whatever you want in there now. I just replaced the letter x with 2x. So I'm under obligation to replace this letter x with 2x. Put a 2x in for that. This letter x gets replaced for 2x with 2x. Now I do want you to simplify. This is 4 times 2, 8x squared. This is 3 times 2, 6x minus 4. Really, you do need to simplify your result. So it is interesting that you can plug all sorts of interesting things into your function, even stuff like that. Let's go back to the function definition so we know what to do here. You need to take your input and square it. This, though, is your input, isn't it? You need to triple your input. This is your input, and then always subtract 4. We got a lot of simplification to do here. Square binomial, quickly. X squared goes here, 1 squared goes here, and if you want that elusive middle term, one of each, please. 2 times 1 times x is 2x. And then, of course, I have 3x plus 1s over there, and now let's run that distributive law through. So this is 2x squared, 4x, and 2. This is 3x plus 3 minus 4. We finish up by combining our like terms together, so there's really a total of 7x's, and what do we get here? Plus 1. So that is the f of x plus 1. It looks like an entirely different function. So just keep in mind that the letter x is nothing more than a placeholder for input, and you can literally put whatever you want in there. And it kind of flows through to the other side, and all those letter x's get replaced. Just to kind of prove that point, I mean, if I were to put an asterisk in my function, what would come out? That's what would come out. So we literally put whatever we want in those functions, including binomials, including other things as well. Okay, so that's function evaluation. Now I'd like to talk about determining the domain and range of a function. So I'm going to provide you with a function. And first, let's just check to make sure it really is a function. And the way to do that, you want to do a spot check anyway, plug some x's in, and make sure only one y value is coming back. But what about domain and range? Now, I did say earlier that domain and range do not necessarily have to be collections of all real numbers. So what is domain? Domain is corresponding to your x or input values. And there are some inputs that are bad news for your function. In fact, bad news meaning it'll cause the function to become undefined. What are the two biggest ways that a function can become undefined? Well, the biggest way I can think of right off the top of my head would be divide by 0 would be undefined immediately. That's infinity. The second way I could imagine a function becoming undefined is to have a square root of a negative number that's imaginary. That is also undefined in the real number system. So those are the two things we're going to be looking for. I want to know the x's that make the function behave and give me answers, and I want to know the x's that make it misbehave. Let's get those numbers out of the domain. So let's start with determining domain. Domains are x's. I want you to take a look at this function and tell me which one x value will cause it trouble. And if you look carefully, you'll realize that it's 4. So my domain would be defined as a big bubble of numbers. They're all in here. A bunch of real numbers, except there's one that's not in this bucket. X may not be equal to 4. So 4 is not in here. And you could say all real numbers except for 4. And there's a symbol for all real numbers, by the way. It's an R that looks like that. So that's the domain for this problem. Now, what is the domain? The domain is literally a bucket or container of numbers. I ought to be able to reach into this container with my eyes closed, pick out a number, put it in the function, and have the function deliver the goods, okay? Now, this bucket of numbers has every number in the world, but 4 is not in there. So you can blindly go in there and pick out numbers, and you won't get the 4 because we took it out. That's how you do domain. Let's do another one. Let's use g. G of x is equal to 7 divided by x squared minus 2x minus 3. And I'd like the domain. Every number that makes the function behave or work. And I want to eliminate the numbers that don't. So, what if we factored this thing? I would say my domain is all real numbers except I don't want 3 and I don't want -1. Those are both bad news. There's your domain right there. So we want to extract those numbers that cause the function difficulty. If you really did put a 3 in here, or here, or here, you would have 7 over 0, which is undefined, which is infinity, or could be minus infinity. It's actually hard to tell which one it is. Let's try another one, h of x. Now, this one, there's no worrying about dividing by 0 on this one, but there is a concern with taking the square root of a negative number. Let's just try a few in here. If you put 0 in here, square root of 4 is just 2. I have no worries there. If I put a 4 in here, x equals 4. 4 minus 4 is 0. That's okay. Square root of 0 is 0. But guess what? If you put a 5 in, now you got trouble. 4 minus 5 is -1. The square root of -1 cannot produce a real valued output. So it looks to me like we want to try to avoid any number that's bigger than 4. It doesn't actually start at 5. It starts just beyond the 4. So how would you express that domain? Well, you would want all real numbers x that are greater than 4. I'm sorry, that are less than 4. Apologize. So all real numbers less than 4. Now, how do you find that domain? So what I would do is grab what's under the radical symbol and express it this way. Say in English that you want 4 minus x to always be positive. Because isn't it true you want to take the square root of a positive quantity and not a negative quantity? Now, mathematically, how do we say that an expression is positive? We say that it's greater than 0. Greater than 0 means positive. Now, it can be equal to 0. We're okay with that, too. This inequality just wants to be solved, so I'm going to take away 4 from both sides, and I get minus x needs to be greater than or equal to minus 4. Divide both sides by minus 1. Oh, that's right. I just divided by a negative, so I have to flip the inequality symbol. So it looks to me like x must be less than or equal to 4, which is what we talked about earlier. 4 is actually just fine. 4 minus 4 is 0. 3 is okay, too. Less than 4 is 3. 4 minus 3 is 1. But anything outside of this particular solution set won't work. So 5, 6, 7, 8, 9, they're going to cause you to take the square root of a negative number. This is the domain right here. All x values greater than or less than 4. You can even represent that on a number line if it helps you visualize it. So 5 definitely shouldn't be in there. It doesn't work. That's your domain. What happens when you get a mixture? So let's mix them up together. So if we mix them together and we put division with a square root, we've got some added things to look out for. So let's do this. On the top, I'm going to put the square root of, we did 4 minus x. So let's do, how about x minus 5? We'll try that. Now down below, I'm going to put a quadratic. You got two problems now. Number one, you do not want to divide by 0. So let's say no division by 0. How do we avoid that? By telling that denominator that we don't ever want it to be 0. Now this is a quadratic, and it's not really an inequality. We'll call it like an inequation. You can solve it like a quadratic equation, though, by factoring. We don't want either of those to be equal to 0. So let's set this not equal to 0 and this not equal to 0. So these are the two bad apples that we don't want. 7 and negative 1. These are bad numbers. So we don't want either of those numbers. Okay. That's not yet the domain because don't forget there's a square root, and we don't care where the square root appears. On the bottom, the top, the side, upside down, doesn't really matter. It is a square root, and I need to enforce this. What's under that square root must be positive or equal to 0. Add 5, and we've got the portion of the domain that comes from the radical. All the numbers greater than 5 are part of my domain. So how would we express the domain in its entirety? How about we call it this? The domain is all the numbers that are greater than or equal to 5 except minus 1 and 7. Those are bad numbers. We definitely don't want those. But wait a second. Isn't negative 1 already taken care of? It sure is. This does not include minus 1. But it sure includes 7, so we better omit it from our domain specifically. So let's simplify it by getting rid of anything that's extraneous. And in that case, it is extraneous. Two final things to finish with. We do have what is referred to as piecewise defined functions, and they look something like this. Now, a piecewise defined function is basically a function that is defined for different intervals in our x domain. So in this particular example, we would use this function for all x's that are 2 or greater. We would use this function for all x's that are less than 2. So it's two graphs. They don't overlap necessarily, but we would go here to 1, 2. And the first point I'd put up there would be at x equals 2. I'm supposed to use that function. So 1, 2, 3, and 4. 2 times 2 is 4. There really is a point right there. Let's move on to the number 3. Well, 3 is greater than 2, so we're still supposed to use this. So that's 2 times 3, which is 6. 5 and 6. We'll reach up here to 6, place a point, and then I'm kind of running out of room on that function. But over here is definitely we're using the line y equals 2x. Now over here, for 2 and less than 2, I should be using this function right here. So let's go to 2, and let's do 2 plus 3, which is 5. Now, because it says x must be less than 2, there's actually not quite a point there. There's an open circle there, okay? But we go back to 1, and there should be a point there, and that point should be at 4, which lines up right here. And then go to the 0, and you get 0 plus 3, which is 3, which goes right here. So let's see here. That should have lined up. 1, 2, 3, 0 plus 3. 1 plus 3 is 4. That's good. And 2, 1, 2, 3, 4, 5. I see what I did. That should be a little higher here. We're just kind of getting things a little bit off kilter here. So that point lines up, and our line comes through here and goes to this open circle right here. That should have been a little bit further over. And shoots off in this direction. So there's actually 2 curves, one here and then one over here. And the curves don't intersect each other necessarily. In fact, they pass the vertical line test. If you send a vertical line through, it goes through this open circle here. There's actually not supposed to be a point there. So this is a piecewise defined function. Piecewise defined function, the function is defined for different portions of the x-axis. For x is less than 2, we were supposed to use this line that has slope 1. For x is greater than or equal to 2, we were supposed to use this line that has slope 2, actually. So it's a little steeper. So that's a piecewise defined function. Now, the next thing I want to talk about is if we were to graph a function. One way to do that is to make a little xy table. And we can put some interesting values in for x here. And then we come over here to our graph, and we graph it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have to go way up there to 11. Now at negative 1, 1, 2, 3, 4, 5, we're here. At 0, 1, 2, 3, we're here. At positive 1, we're back to the 5. And at 2, we're up there at the 11. What you got here is a parabola. This is a quadratic, which the shape looks to be like a parabola. And it comes down like this. Now, if you want to know if this curve is indeed a function, we like to apply the vertical line test. So let's start slicing with vertical lines, and you'll notice that by slicing with a vertical line, each time I do that, I touch the curve only once. Every vertical line, I touch the curve only one time. So you can slice it as many times as you want, and we only touch the curve once. This passes the vertical line test. This is indeed a function. Let's say we were to graph a circle. You might remember from the previous chapter how we did this. If you graphed a circle, this is the equation of a circle. Let's see if it's a function. So H and K are right here. R is right here. So let's go off to 1, 2, negative 2. Mark off our center. Radius 2. We go up 2 units. We go over 2 units. We go down 2 units. And we go over 2 more units in this direction. And we've got ourselves a circle. I'm sketching that in right now. It's the shape of a circle. Will this pass the vertical line test? I think not. Okay. So if you want to try the vertical line test, why don't we slice right here at x equals 2? How many times did we hit the circle? Twice. So at x equals 2, there are two answers. There are two y values. Y equals 0 and y equals minus 4. Failed the vertical line test. So a circle is not a function. Definitely not a function. The other thing you could do is plug the 2 into the original equation, and what you would get, let's put the 2 in for x, you get 0 here, and you would get y plus 2 squared equals 4. Let's try that out, see what happens. Take the square root of both sides, but when you take the square root of that side, square root of this side, you get a plus or minus, and you get y equals negative 2 plus or minus 2, which is 0 and negative 4. I can tell you that having a y squared in a relationship usually is a giveaway. It's not a function. And you can see that it fails the vertical line test. Okay. So we've talked about evaluating functions, finding the domain, and I think the last thing I'll do is look for domain and range on a graph, and we'll finish this video up. So if I were to provide you with a graph, this is something we do more in pre-calculus than anything else, but let's say I had a graph that started here and went that way. And it peaked off here at y equals 2. And this was x equals 1. Well, your domain is represented on this graph in the x direction, left and right. Just observe what x values showed up. X equals 1, x equals 2, x equals 3, 4, 5. They're all on the curve here somewhere. So your domain is all x is greater than or equal to 1. The range is the range of output values. What y values are you getting? Now to do that, you want to look up and down to find your range. And I think what I see on this graph is that my y values peak at 2, and they go all the way down to negative infinity. So I think a great expression for range here would be y is less than or equal to 2. So that's determining domain and range just given a graph. Okay, we'll finish up this section, P3. We're going to look next at transformation of functions. We're going to look at composite functions and the zeros of a function. We're going to finish that up in the next video. Thanks, and we'll see you in the next video.